Now, because the population is large, what we do generally in statistics is go out, collect a sample, and from that smaller subset, the sample, we're going to do some calculations that's going to tell us about the population. Now, there's something in statistics, it's called a point estimate, and it's a general term. And as far as this course is concerned, there's really only two points estimates. The first one that we look at is X bar. And I meant to take and try to make this into a real X bar here rather than write out the thing X bar. And let's see if I can do that real quick. I don't know. I was out here this morning trying to hone things, but it doesn't look like the internet's going to cooperate. Let's see. In order to get these funny symbols, you got to do programming, which I know how to do. It's just that, I don't know. I'm not going to worry about it now. But anyway, you know what X bar is. It's the X with the line over the top. That's the symbol for the sample mean. And it's important to distinguish that from mu, which is that, Greek-looking U thing, which is the population mean. All right. So what we're going to do with this point estimate is we're going to use that X bar to give us a range that we can feel fairly confident about that population mean. We don't know that. Now, the confidence interval is an interval that's just going to be used to estimate. We're not going to be able to get it exactly. If we had the entire population and we did the crunching on it and calculated the mean, we would know what it is. But in general, we're not going to have that luxury. We're just going to be working with a sample. Now, a confidence level is a percentage, generally between 0 and 100. Generally, it's going to be in the 80s or 90s. You might have some going down in the 70s. But the reason why it's between 0 and 100 is because we can just have a certain percentage of confidence, because it can be technically anything in there. You'll never get up to 100%, and also you'll never get down to anything probably below 50%. Now, each level of confidence has its own critical value. Now, you already know this, and you've already done this in the backwards thing. When we're talking about a percent, as in a percentile, if you wanted to know, like, say, the 75th percentile, which is also the third quartile, you would just look up 0.75 with your inverse norm, and that's going to give you a z-score. And that's what's called a critical value. Critical value. And that critical value is really the only kind of and you already know how to do that, but here we're putting together the critical value with something called the margin of error. I'm sorry. We're putting it together with your standard error to create a margin of error. So you remember this, the standard error, that's what 6.2 was all about. So what we're going to do is we're going to put together the standard error and the critical value, multiplying them, and that's going to give us our margin of error. And all that is just a comfort zone. So as I might say is in this little picture here, the thing that you're trying to estimate is the mean in this first case, the population mean. So the estimate, what we're using is the X bar. So what we're going to do is have a little bit of a margin on each side that tells us where we can safely say that the real mean, the population mean, lives. All right, now for the mean, all right, let's see. I probably should type something else in here. Confidence interval. Let me see if I can do that one real quick. The what do they call it? I think they just call it mu. Yeah. I can do a little bit of magic here and you can be able to see it. Alright. So if I did this right, it's going to turn to a mu. All right. So there's your mu. Okay, that's what we're trying to estimate. But since we don't know what that is, we're just going to have to use X bar to do it. The way we handle this is we're going to take the X bar, the sample mean, and plus or minus our what we call our margin of error. The circle part is the margin of error, and that's what this is over here on the right. And so once we figured out what that is, and notice that all the way to the right over there, that sigma over the square root of n, that's what 6.2 was about with this thing called the standard error, right? And we need to do that just because when we're going in and we're pulling out a sample, it changes things based upon the sample size. And that's why you're dividing by that square root of the sample size. And that z of alpha over 2 is simply the critical value for whatever confidence level we want. All right. Now, I think I might have said this up there. I'm not 100% sure, but there are various levels of confidence. The 95% level of confidence is the most common, and it can be looked at like that little picture. All right. 95% level of confidence. Remember this from your empirical rule. Your empirical rule had 3 different scenarios. You had 1 standard deviation from the mean, which was 68%, 2 standard deviations, which was 95%, and 3 standard deviations was the almost all. Now, the reason why 95% is important is because if you've got 95% of anything, you've got most all of it. You know, let's just say you had a debt of some kind and somebody owed you some money, and you got 95. Let's say they owed you $100 and you got 95. You'd probably be fairly content with that, especially if you had to go through some trouble to get it, which is what we're going to have to do here, is go through a little bit of trouble. So that 95% relates to 2 standard deviations from the mean. Now, you've probably seen this little thing pop up from time to time, asking if something is unusual. Well, we've been doing that, I think, since chapter 3 on and off. And something is unusual if it's less than 5% of the time, or 0.05. Well, that relates to 2 standard deviations from the mean. And that's why z-scores are so important. Remember, a standard deviation is essentially a z-score. It tells us how far away from the mean something is. So if we got a z-score that relates to 95, more than 2 standard deviations, we start to get into rare territory. Here's some other ones. You might see some of these in the homeworks, just to kind of torture you a little bit, but most of them are going to be 95%. So when you're talking about the percentage, well, just remember, in math, you can't really work with a percentage, so you work with 0.8 or 0.9 or 0.95, 0.98, 0.99, and so forth. And then if you were to look those up, then you would get back the particular z value you wanted. Now, I'll show you how that works in a bit. But in most part, you don't need to really remember this, because on that exam sheet, and I think it's actually easier to look on the sheet than it is to do the calculator for these, because you got to do the 1/2 thing. because let me just kind of reiterate up here. We looked at this in chapter 6. But if you've got that middle 95%, that means that 5% is broken in two. So you got 2.5 on the left and 2.5 on the right. So what you have to end up looking up is the 0.025 or the 0.975 to get these. But anyway, this is on that exam sheet. This is not anything you have to remember. So if you go to the bottom of what they call the T-table, and I'll show it again to you in a bit, the whole thing. At the very bottom, it's got the 95%, and you can see right above it is a 1.96. 90% is 1.645. So these two right here are, usually the ones that are used the most often, the 90 and the 95%. Now you can do any one with the inverse norm by, like for example, 96 wasn't on here. So if you need another one, you can go and do the inverse norm as such. Inverse norm, put it in the area, and then leave 0 and 1 alone. Like I said, if you wanted a particular value for your data and you had a different mean and standard deviation, you can put them there. But you got to understand that that's, like I said, it's kind of doing all the in-between for you. All right. We're going to go through example in a bit, but I just want to get a little bit of the theory under the belt before we do. Now, there's a trade-off when you have a higher confidence level versus a lower confidence level. When you've got a real low confidence interval, and they use 70% here, the margin of error is fairly narrow all the way on the left. And all the way on the right, if you've got a real high confidence level, and that one is the 99.7, that's the almost all. Notice that the margin of error is wider. So 95% ends up being a good compromise for most folks. And that's, like I said, that's what almost always is used in practice. If not, it'll be because there's some other kind of specific reason for it. Because, like I said, most of the time people are content to be 95% confident. You can never really be 100% confident. It's always a little bit of a possibility of error. All right, so let's look at this example. Now, keep in mind, let's see, where did I put, I want to back and reiterate something. Okay, right up here, I didn't really key on this, but this is what I call the theoretical case. And this is going to be useful because this is how pretty much all confidence intervals are done in one general way. But this is also something that almost never happens, because in this case here, which is what 7.1 is about, is that we know sigma. And if you remember, sigma is that little kicked over 6 looking thing. And again, the Greek symbols always refer to the population. Now, the reason why I say this is theoretical is because if we don't know anything about the mean of the population, most likely we don't know anything about the standard deviation of the population. But if we've got it, then it's really a pretty easy thing to do. And that's what this case is about. That's why I'm calling it the theoretical case. So let's go back down here and look. All right, so a machine that fills cereal boxes is supposed to put 20 ounces of cereal in each box. A simple random sample of 6 boxes is found to contain a sample mean of 20.25 ounces of cereal. So that's the X bar there. All right. X bar, sample mean. It is known from past experience that the fill weights are normally distributed with a standard deviation of 0.2 ounces. See, there's a couple important things here. First of all, everything we need to know about normally distributed, we got to know that. In 7.2, we're going to also look at, if we don't know that it's normally distributed and the sample is small, then we're going to have to check normality, which is what 6.5 was all about. But right now, we're just presenting that everything is nice and neat. Now, construct a 90% confidence interval for the mean fill weight. All right, so remember, for everything in the entire book, you got to have a simple random sample. That's just kind of a given. Now, here's where we got to know one of two things. The sample size is large, in other words, greater than 30. In this case, it's not because it's 6. But we were told that it's normally distributed. But because that's one of the options, either large or normally distributed, then we can proceed. All right. Now, sometimes it can get confusing, at least it does for me if I've kind of stepped away from this for any length of time. Okay, the one that we're looking at on the left is 0.9, and that's the one we're looking at for the 90% confidence level. And the 95% is the one on the right. Now, it can get confusing, so let's kind of go through this. The one we're dealing with is the purple one. All right, so that means then 90% or 0.9 from one means that there's 10% that's on both sides. But because this thing is equidistant, and this is why you had problems in chapter 6, it says find the z-scores for the middle whatever percent, 70%, 88%, and so forth. You got to find those two endpoints. All right. Now, the good thing about it is they're symmetric, but I'm going to show you kind of the way to do it, of the short, the short way and the long way. And I think I already did this, but I want to reiterate. Now, we got to take that 0.10 or 0.1 and divide it by 2. So that means that 0.05 is on either side for the 90%. Notice the one that we looked at before, probably last week, it ends up being half of 0.05, thus the 0.025. And if you look that up, you would get the negative 1.96. And if you take my advice, you could just lop off the negative sign. But anyway, if we look up 0.05 or 0.95, which is 0.9 plus the 0.05 over here, then we're going to get the value we need. So let's just take a look at the calculator, and then we'll look at the table. I got a table here somewhere. Where's that table at? Oh, it's way down here. I put it in there this morning. All right. Now, the good news is, like I said, for most of chapter 7, you're just going to deal with a couple of critical values. In chapter 6, they, make you chase them all over the place and do different ones. But let's see if I can kind of explain this to you, and then we'll look at it with a calculator. So anyway, what they call the alpha Hold on a second. I'll fix this for you. So, it's not something different. Oh, let me see what I got. Wrong symbol in there. Supposed to be the dollar sign on both ends. Okay, so there's your little alpha thing, and then this is alpha over 2. And this is going to magically turn into what we need. Let's see if I can get this real quick. Should do it, but I didn't do what I wanted. I'll just take that. Don't worry about it later. But anyway, that's what we call alpha over 2. You know what? This is alpha over 2. There we go. There we go. And then this just your endpoint, what you're looking up. This is what you need to look up. All right. So, like I said, let me show you this table, and then I'll show you the calculator. I really think, for the most part, in this case, because you're dealing with things that are common, that the table would be. Let's see if I can get this bigger. All right. So if you go down here at the bottom, you can find that 90% is 1.645 with no problem. But notice, as I said up here, you can kind of look at it two ways. And usually I think with the table that you got on that sheet, it says 0.05. That's the amount in just one of the tails that I showed you. So you can look at it either from the top or the bottom, but they all lead you to the fact that it's 1.645. Now, the bad thing about the calculator, and I'll show, is you've got to put in that 0.95 that we just figured out. Like I said, there are some instances where the calculator is not as easy as you would hope it would be. So the second vars. So what I got to put in here is 0.95. And let's leave the rest of there. But if I do that, 1.644, it's a little bit more accurate here, but that's essentially the same one. 1.645 would work. All right, so you got to do that little thing that I showed you, where you do the half and add it to the 0.9. So the half of 0.1 is 0.05. And so that's what you have to look up with a calculator. The good thing about the tables is that it's a little bit easier. Look one more time. You know, down there at the bottom, you look up 90%, and you can see right up above it to use 1.645. So then, and then that's how they get the 95, 1.96. And the reason why I covered those two situations of 90 and 95%, because it's easy to get them confused. Because the 95, if you look up 95 on the inverse norm on the calculator, you're going to get the one for 90%. So like I said, it's much easier to go to the table and figure it out. Because like I said, you got to take that half and add it to the 0.95 to get the 0.975. And like I said, when you add half of the 10%, you get 5, which brings the 90 up to 95%. So it can get confusing. So this right here, I think, works the best. All right, so let's go through that problem that I had. Took a little bit of a detour there, but I want to make sure you understand some of the pitfalls here. All right. And I'm going to put right here, or the table is clearly marked for 90%. Either way. All right, so let's look at this problem. Simple. Okay, so we're in the middle of that problem. So we're dealing with 1.645, and we'll see it here. They show us what I just showed you. All right, on that table at the bottom, you can go up from 90% and see this 1.645. Now, you also got to calculate the standard error. So that's going to be that standard deviation that was given, the 0.2, divided by the square root of 6, and that comes out to 0.08165. All right. Let's see something. And that's rounded off to 5 decimal places. I don't know why they did that, but generally speaking, you want to go out as far as you can, and then when you round off to whatever you're asked. Always go a few decimal places beyond what you're asked to round off as. Because what happens is, if you round off, let's say it says give your answers to the 100th place or the second decimal place, as we're going to see. If you round off to the second decimal place immediately, then you lose accuracy, and so the final answer is not going to match when you're doing it on a computer. And that is important. It's just that never round off too early if you're doing things by hand. All right, so we got the standard error, which is what we did in 6.2, and we're multiplying it times the critical value of 1.645, and that gives us 0.1343. That's what we call the margin of error. Now, for the most part, we're done with all the mean nasty things, because we've found our critical value and we've calculated our standard error, and we've multiplied those two. And so the margin of error just needs to be subtracted and added to that X bar up there, the 20.25. So X bar plus or minus 0.1343, or in this case, 20.25 plus 0.1343 minus 0.3. So if we subtract 0.13 from 20.25, we get 20.12. All right, that's on the lower side. And on the higher side, when we add 0.1343 to that X bar, we get 20.38. So what that tells us is we've got a 95% confidence level that the true mean is between 20.12, 20.38. Now you can carry this back to our original M&M sampling thing. we had, as I tried to show you, none of them came out to, well, very few of them came out to exactly the right percentage that was the population. And we kind of knew that. We weren't trying to find it out because the mean we already knew. It was established. So I was just trying to show you how we come close, especially the more items we put in our sample. But what this is telling us with this 90% confidence interval is that we're fairly confident that the true mean, in other words, just based upon these sample of 6 boxes, is we've got true mean of 20.12 to 20.38. And what does that mean? Well, that's good news for the manufacturer because it looks like, based upon this sample, that they're not shortchanging anybody on the 20 ounces. They got a little bit more in each box for the most part. If, for example, the left interval was, 0.19 something, then that means they would be maybe shortchanging the customer. But this is good news because the 90% confidence level shows us that the mean of the population is between 20.12 and 20.38. All right, questions? Like I said, that's really what we would call a very theoretical for the mean. All right. Now, the procedure is going to be exactly the same for the non-theoretical. It's just that what is usually the case is we're not going to know what that population standard deviation is. We won't know what sigma is. So what we got to do is make a couple of adjustments, and it's not as bad as you might think. Oh, well, first of all, let me just talk about this, about the sample size. All right. Just take you through this, and then we'll look at, because there's one thing I want to tell you about this that's important. Let's just say that we want to know what size of a sample we need in order to have a certain level of confidence and a certain margin of error. All right. Now, on that second line here below where it says sample size, that's the margin of error formula. It's the critical value times the standard error. All right. Now, if we solve that for n, which involves squaring both sides and then multiplying by n and all that, then this is what it looks like on the third line there. All right. You don't have to worry about doing that solving, but that's just where that comes from. It's sort of like the z-score, the backwards z-score. All right. So what that n just essentially means is that's the size of the sample we're going to need. So you would have to be given the confidence level. You would have to know what sigma is, and you'd have to know how accurate you want it to be, which is what m is. Now, here's the thing is, you always got to round up on these things, and let me kind of show you. And I'll do it over on the board because this is something that's can't really type out. But we got a situation here. Scientists want to estimate the mean weight of mice after they have been fed a special diet. From previous studies, it is known that the weight is normally distributed with a standard deviation of 3. We got to have that standard deviation, and we should know that it's normally distributed. How many mice must be weighed so that a 95% confidence interval will have a margin of error of 0.5? So let's go over to the board. All right, so this is fine sample size. I don't know why this thing always defaults to red, but all right. We know that sigma is equal to 3 And then what was the other thing? It was 0.5. M, margin of error. And we want 95% level confidence. Now we got everything we need. So this means the critical value is 1.96 because that's the level, that's the value you get on that table. Let me just show you. 95%. 95%, 1.96, okay? That's the most common one. All right, so now we're just going to go ahead and do the calculations. Like I said, I can't really type this out, so. Let's see, it's, so this is the formula. All squared. So in our case, it's 1.96 times 3. And then we got 0.5 down here. And then this is all squared. Now I'll spare you all the details. But if we do that, I'm going to do it on the calculator over here. I should know what this is since I've already done it, but 1.96 times 3 divided by 0.5. And then we square that. And that comes out to 138.30, let's say. All right, now, this is why it's kind of important to understand the difference between discrete and continuous, because if we're talking about mice and sampling mice, or if we're sampling people, then it really does us no good to be able to deal in partial values, because there's no such thing as 0.3 of a mouse, just like there's no such thing as 0.3 of a human being, because you can't really work with that. So what you got to do is you have to bump up to the next whole number. All right, so you always bump up to the next whole number. Doesn't matter what it is, if it was just a little piece, like in this case. So, and probably if you took college algebra, they might mention it, the ceiling function, it's also called. So just remember that. When you're talking about rounding here, it's a little bit different than when you're dealing with general decimal and you're asked to round to a specific decimal place. And it's just, I guess you would say, it's almost like a common sense thing, because you can't, if you were to just lop it off and survey 138 mice or sample 138 mice, that's not large enough, because we got to have that third of a mouse in there, and the only way we can do that is to go up to the 139th one. All right, so let's jump back over here. All right, we're doing all right on time. Okay, and then we'll cover this. Now, here's what's most likely to happen when you're talking about the mean. You don't know that sigma. So what you got to do is calculate the sample standard deviation. In other words, just like you do for, in fact, we looked in the last problem, we had the sample mean we were using. Well, it's just that here, if you don't know the sigma, you got to use the sample standard deviation. And if you do the sample standard deviation, then what you got to do is notice that on this little confidence interval formula, there's a T there now, and it's not Z. All right. Well, it's a little bit hard to explain, but the T of distribution it's kind of a subset of a bunch of standard normals for different sample sizes. So as I've said is, and this is something I don't know if you'll see it in the book, but I've got a feeling that once I come up with the idea, I'll start seeing it in the books, because that usually ends up happening for some reason. Somebody's out there selling my information to these book people. But anyway, what it amounts to is when your sample size is small, you remember, like in the case of the standard deviation, sample standard deviation, you have to subtract one. And I told you that that is simply to err on the side of confidence. So when your sample is small, you're essentially going to have a wider or a larger standard deviation just to be safe. Well, the same thing is going to happen here. All right. We use something that called degrees of freedom, which is essentially n minus 1, like in the sample standard deviation formula. And so when the sample size is small, then the curve is not quite normal. But as we get larger and larger, it starts to conform to the Z table or the standard normal table. So what we're going to do is err on the side of the caution and use this called student's T distribution. I don't know why the student comes from, but they usually just call it the T distribution. Now, if you're playing with a calculator other than the TI-84 Plus, it may not be on there. They'll have the one that says 5, the T PDF and the TCDF. But I keep getting reminded of this because the students that are using other calculators, and the TI-83, for example, doesn't have the inverse T. But you're not really at any disadvantage, because for the most part, you can go and look at the table. And I got the table right here. It was what I used before, and I'll kind of show you in a minute how it works. All right. Now, the assumptions are the same. In other words, you got to have simple random sample, and you got to know that it's normally distributed, or you got to have a sample size that's greater than 30. All right. So if we don't have a sample size, and I know there was a question in chapter 6, it kind of threw me off when somebody was bringing it to my attention last night about, I can't remember the number, or it might have been number 3 in 6.1. And it said something about you have a sample size of 15 and your standard deviation is this and your mean is that. Is it appropriate to use the normal deviation, the normal table? And the answer was no. And I kind of on first pass thought something was wrong with it. And essentially the answer was no, because the sample size wasn't large enough, because you got to have larger than 30, or you got to know it's normally distributed, and they didn't tell you that. So it was small, so you couldn't use the normal distribution. So all that still comes into play. Now, this is the same thing that could happen in the very theoretical case, but usually you've got a, 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 a set of data. Remember up there we had 6 values. They told us what the mean was, but sometimes you may have to calculate it on your own, and you may also have to calculate the sample standard deviation. And this is a good time to have technology on your side, because that, that sample standard deviation takes a while. Now, here's where the things are different. If you don't know sigma, if you don't know the population standard deviation, you got to go to the t-table with degrees of freedom, which is n minus 1, and then you calculate the standard error the same way, except you're using the sample standard deviation because you don't have the population standard deviation. And then you multiply it by the critical value from the t-table, and everything after that's the same. You just add and subtract to do it. So let's look at this example. Now, just to remind you, the common theme in 6 and 7, or one of the themes, is if the sample is small, less than or equal to 30, then we have to check for normality before we proceed. So keep that in mind. That first problem, it told us it was normally distributed, even though it was only like 6 pieces of, data. All right, so now a food chemist analyzed the calorie content for a popular type of chocolate cookie. The following are the numbers of calories in a sample of 8 cookies. And you've got them lined up there. And it says for us to find a 98% confidence interval for the mean value of calories in this type of cookie. So the assumptions is simple random sample, which was a given. Because the sample size is small, the population's got to be normally distributed. They don't tell us that. So we got to look at something. They give us the dot plot for it. And usually I think all the ones you'll have in 7 and 8, they'll give you something, either the standard normal, either the histogram or dot plot. You can use the QQ plot. I pushed that if you look at mean and median are the same, that's also good. But you don't have the median in some of these, so it doesn't going to matter. You're not going to be able to use it unless you calculate it. But anyway, they also calculate the sample mean and then the standard deviation for that sample. So it's S, not sigma, but we're going to use it like it was sigma. But we go to the t-table in order to compensate. Now, you notice on that dot plot, there's no skewness, there's no outliers. As a matter of fact, you've got one mode right there in the middle, which is good. At 116, there's 2 of those. So it's pretty good. All right, so here's what we do. The number of degrees of freedom is n minus 1. So there were 8 pieces of data. Subtract 1 is giving you 70. Now they show you the snippet, but I'm going to take you back up here to the full table. And show you. Now, the first thing you want to do is find your degrees of freedom. All right. So if we go over here on that column all the way to the left, and this is a PDF, so I can't select it. But you see the degrees of freedom over here. It's all the way to the left. You got 1, 2, 3, 4, 5, 6, and 7. Now, there's kind of 2 ways to do it. What did they say the percent was? 98%. Well, in order to avoid confusion, if you go all the way to the bottom, you got 98% right there. That's the easy way to do it. If you were to follow that all the way up, just notice that that's 1, 2, 3, the 4th column from the right, so we don't forget what it is. So 1, 2, 3, 4. So notice that that is 0.02 and 2 tails, or half, 0.01. So when you come over to 7, it's 2.998. 2.998. I think the table is the best way to go on this, but I'm going to show you with that calculator. But like I said, if you don't have the TI-84 plus, the function is not on there. Because it must be a difficult thing to put in there. I don't know why they haven't gotten it into any of the lower ones. Did you have a question, Holly?
I did, Mr. Cruz. What are we trying to find right here? We're trying to find if we don't have sigma. Am I right?
Exactly.
Okay.
We got to compensate for that. And essentially what it is you'll notice that as the degrees of freedom get smaller, the critical value gets larger. But as you come down, let's see, we're on the fourth one. See how it comes out, and it ends up being 2.326 is the one that would be from the Z table.
Yes.
So what we're doing is, as that sample size increases, and it's called degrees of freedom on here because it's one less, see that number gets larger? Like I said, it's to err on the side of caution, if your sample size is small. And as your sample size gets larger, it's going to eventually turn into the one from the Z table. So that's really all you're doing, is you're getting a different critical value from this table because it's just an error correction.
Okay. Thank you.
All right. So also show you on the calculator. And like I said, if you don't have the TI-84, you're not really that much of a disadvantage. But all right, so let's look this up, and I'll show you it's the same thing pretty much. And I think for the most part, all of your problems, you can use the table in this chapter 7 when you're dealing with the t-table. So second vars, and notice that right below inverse norm is inverse t. So again, if you're using the calculator, you gotta make sure you're doing the adding the 0.5 back. So we're going to put 0.99 because 1 minus 0.98 is 0.02 divided by 2 is 0.01 added to 0.98 gives us 0.99. I know it's confusing, but that's the way the calculator does it. And then we got to put our degrees of freedom. And it takes a long time to do it. So maybe it's just a complicated, I can't believe that anything nowadays with calculators is that complicated. But see, it's the same one, the 2.99. Oh, I'm sorry, 2.98. So it's just kind of, this is the calculators are not all that much of a help in most cases, because they kind of compound things. If I were going to do it my way, I would just kind of always do it with a spreadsheet, because at least with a spreadsheet, you don't have to worry about inputting things so well. You can copy and paste and not worry about mistakes. But anyway, let's see, what were we doing? We were over here looking at that problem. So there's the value we're talking about, the 2.998. Same thing we got when we looked it up. And this is why, as I said, if you look up at the top, you can't see down at the bottom. Well, they got it right here. The 0.98 and twice the 0.01 add up to 100. Okay? Or 1. But they only give you, on the official table, the one that the book uses, they give it up here half of the alpha over 2. But like I said, if you use the bottom, then you can't really go wrong, because like I said, it lines up that way. All right, so we had an X bar of 115.375, an S of 2.8253, and an N of 8. Notice that now when we go back to do the calculation, we go back to the N, not the 7. That was the degrees of freedom that we just looked up in the table. So the 2.98 is the critical value. The standard deviation was 2.8253 divided by the square root of 8. Multiply those, you get 2.9947, almost 3. And then we just simply add or subtract and add to the 115.375. And that gives us 112.4 to 118.4. So the 98% confidence interval for the cookies, the number of calories in each cookie is anywhere from 112.4 up to 118.4. And what that's done, because we went up to 98%, that confidence interval has gotten wider. If you were to do this again with the 95%, it would be smaller. All right. Let's see if we can finish this one and then have a break. Because I want to do another one, because like I said, 7.2 is really the meat of the section, because for the most part, you always go to the t-table. And if you got a large sample, you can go to the z. I'm sorry, not a large sample, but generally if you got a sample size that's over 200, the value is the same thing as the z. But let's do one more of these, and we'll do it on the board. Okay, we want to create a 95% confidence interval to estimate the mean income of doctors who earn their degrees from public institutions. Now, we sampled 50 doctors, and that's important because now we got a sample that's large, so we're not going to have to worry about normality. And from that data, we have a mean of 145,580 and a standard deviation of 13,200. Notice that both of those values come from the data of 50. So should we use the Z or the T table? Well, we're going to use the T because we do not have that sigma. All right. Which, like I said, that's status quo. That's usually what's going to happen in real life. All right. So let's go look up 95%. Okay, we're going to write on that board what we know. Make a fresh thing. So let's go back and look. Is equal to, and that's the sample standard deviation. It's coming from the sample. We want the 95% confidence level. All right. So let's go over to that tool. All right. So I'm just going to kind of do it the easy way. If you want to do it with the calculator, you got to remember to put in 0.975 for your area. But we're just going to go down here where it says 95% at the bottom. I said I wish you could see my cursor, but it's in that fifth row over, right above the L in level, the ending L. And if we were doing with the Z table, or if we had a sample that was, few hundred, we could just use 1.96. But remember, our sample size was 50. Now, 50 is not on here because the way this table works is it goes from 1 to 30 by ones. And after that, it starts skipping to tens. All right. So, like everything else, and what this table does is it errs on the side of caution. So, you don't go up to 60, or if you had 50, you wouldn't go up to that. You go to the next lowest one. So, we're going to go down to 40, and we're going to use 2.021 as our critical value. Not 1.96, but 2.021. And that makes sense because it's based upon sample size, so it's a little bit larger than the critical value if we were using the Z, if it were a perfect world, because it's not a perfect world. All right. So there's the value we're going to use. We got this, we got this, and we got that. Once we figured out what the critical value is, the 95% doesn't really matter anymore because we've already. So these are what we're using. So let's just write this out. Our error, or margin of error, whatever you want to call it, is equal to the t of the alpha over 2 times the standard error, which is s over the square root of n. Same thing, it's just that in this case, because this imperfect world thing, not knowing that sigma, we got to use s. So we got everything here now, so let's just fill everything in. And then the 13,200 over the square root of 50. All right, I'm going to do it on the calculator, and then I'll write in. You can try to follow along if you want. I'm not going to show you that because it takes too long to bounce back and forth. So this is that's 1866.76. And this is just generally what happens whenever you're using the standard error. It changes. It makes the standard error is smaller now because you're dividing by that large of a number. So as your sample size increases, it's going to make that standard error larger. And that's just to account for the fact that it's going to change when you're pulling out a handful. And the larger the handful is, the smaller that standard error is going to be. So now we're just going to multiply that times 2.021, and we're almost finished. So that's 377.2 and 73. I'm going to put the cents in there, but when we get to the end, we're going to round it off to just whole numbers. So that standard error is $3,772.73. All right, so that's what's just going to be added and subtracting. Let's see, 145, 580 minus 3772.73, and I'll put a comma there, 145 plus. So that's what we're going to do, and then that'll give us our confidence interval. So on this side, it's easier to do the adding first. Hold on a second. Oops. Hold on a second. Do it again. Something doesn't seem right. So I'm just adding first. So 149, 352, and then 73 cents. I'm going to just round that off on the final one, but over here, it's 145 minus. So 149, 141, actually. 807.27. So there's our confidence interval. You can write it like that. There are different ways you can do it, but I think the way that the book tends to do it is like this. Remember, this means between. So so there we go. There's our confidence interval. Like I said, and that's really the hard part. Like I said, is because in reality, you got to go to that t-table and like I said, if you've got everything perfect given sigma, then you don't really have to do that, but that's rarely going to happen. Except for a textbook problem, you know. All right, any questions? Pause this. If you got any questions, let me know. We'll probably finish and have enough time to still have a question and answer session. All right, so let's go back over to those notes. And we'll look at the last scenario. And we're dealing with proportions. Now, as I had said before, a proportion is really the same thing as a percent, and it's kind of the same thing as a probability. So what we're dealing with there is something like 16% or 15%. Like if we were dealing with smokers, most likely I think the most proportions give about 17% if you're talking about the percentage of people in the U.S. that smoke. That's a proportion. You can also write it as a percent by, going 2 decimal places and adding the symbol to get 17%. 0.17 is 17%. So what we're going to do here is this is something where we don't have a mean and have a standard deviation. In that case, it's real easy what we need to do, what we can do. It's not hard at all. The good news is you always use the z-table. So that old friend of 1.96 for 95%, always there. You don't have to get a different value depending on degrees of freedom because that's not used here. Now, the one thing that's different for the point estimate, we're not using X-bar because we don't have an X-bar. But they call the point estimate here, they call it P hat. See that little P has got a little cone over the top. Let's call P hat. And what we're doing is we're estimating the population proportion. And it looks like a P. It's most likely what it should be is a rho, which is a Greek symbol, because like I said, all of the population usually are Greek. But that is its counterpart for the sample. And the way that we find that P hat, if we're not given it, is just like we would do a probability. In the denominator is the total number of the sample, and in the numerator is the total number of whatever it is we're dealing with. So like I said, if we were dealing with smokers, X would be the number of smokers in the sample, and N would be the number in the sample. And you're going to get a proportion that's less than 1, most likely. I mean, very, very rarely would you ever get a proportion of 1, because that's the extreme end. Just like you'd rarely ever get 0. Now, there is a central limit theorem for proportion, and I think it's 6.3. We didn't go over it because I don't really see why. But you got to just use this as a formula instead of the proportion, the central limit theorem for the mean. The way it is done is pretty simple. It's a square root, and in the numerator you got P hat times 1 minus P hat, divide by N, and then square root. And then you just take that and multiply it times your Z value, and you got your margin of error. You add it and subtract it to your point estimate, your P hat, and that's going to give you your confidence interval. The assumptions are slightly different. Sample, random sample, of course. And like I said, the population is at least 20 times as large as the sample. All right, that's something that's kind of, those first two, we're almost going to have to just assume, okay? Because these are all theoretical problems that, you're handed to. And I'll show you what I mean in a second. Now, the items in the population are divided into 2 categories. You got to have a yes, no. You got to have smoker, non-smoker. You got to have male, female. You got to have, just like with the binomial thing, you got to have, you're going to win a burger or you're not going to win a burger. It's 2 categories. And your sample can't be too small. And the way they judge the too small is just that there's got to be at least 10 individuals in each category, which means that at the very least you can't have a sample that's less than 20. So, but most likely, if you got no's and yeses, they got to have 10 of each. So here's a little example. And like I said, for the most part, other than what I showed you on that, what they call the standard error for the proportion, it's very much the same thing, except that you don't have to worry about standard deviation and mean. All right, so in a survey of 517 music teachers, 403 said the video games Guitar Hero and Rock Band have a positive effect on music education. All right. Now, construct a 95% confidence interval for the portion of music teachers who believe that these video games have a positive effect. Now, as I said, you're always going to go to the Z table here. So for the 95% confidence interval, you're going to use that familiar 1.96 here, because that's the same thing. And a matter of fact, in that last problem we did with the doctors, we didn't use 1.96 because we had a small sample size. So we had to adjust for the sample size. So it was a little bit larger than 1.96. It was 2.02, I believe. So let's look at how we're going to proceed with this. First of all, you got to check the assumptions, simple random sample. If you don't have that, you can't move forward. So we got that. And they say it's reasonable to believe the population of music teachers is at least 20 times as large as the sample. Now, they don't tell you that, but like I said, as those two things, you're always going to assume in this course. The simple random sample you have to, you can't go anywhere. Now, the items in two categories. Now, think about this. You have those who think that this program or this video game has a positive effect, and you have those who do not believe it is. So since we know that there are 403 people or teachers that like this video game, then there are 403 minus 115, which is 114, who do not. So that helps us see that there are 10 in each category. All right. Because we got 403 in the yes, 114 in the no. So we got the assumptions. Now, we got 517 and 403. That allows us to calculate the p-hat. And I'm going to go ahead. It's not fad, it's p-hat. Why are they doing that? It's 403, 517. And like I said, if you calculate that out with the calculator, you're going to get a proportion. And that's why it's called p-hat. The p stands for proportion. And we want to find the confidence of the population proportion. So 403 divided by 517. So that gives us that, what they got down there. All right. So they got it right there. The N is pretty simple because there were 517 surveyed. Now, from that, we got everything. We don't even need to have all those things that we had before. Now, for the mean, because for the mean, you had to have the standard deviation, and you had to have the mean, and you had to have the sample size. Here, it's just the sample size, and then the p-hat, they call it. Hold on a second. Hold on. I was going to try to make those make that into a real p-hat if I can do it real quick. If I had time to experiment around, I would just go ahead and try to do it, but from my memory, but oh well, it's not going to be too cooperative. So anyway, so that's the p-hat right there. Like I said, I just had to write it out because that. Now 1.96, you can go to the calculator, you can go to the table, but no matter what you get 1.96. They show the table, and like I said, they go all the way down to the bottom and at 95%, and that's the 1.96. So the margin of error is going to be the critical value times that standard error, they call it, 1.96 times. And you'll see the one thing that's peculiar about this book is they always put 1 minus p hat. That is essentially the same thing in some books as q hat, because the probability or the proportion of something happening and not happen have to add up to 1. So that, again, that's the complement rule in play there again. So when you do that, you multiply those two, then divide by 517, and then you take the square root. Since we got plenty of time here, I'm going to just take you through it on the calculator so you know I'm not pulling any funny business, or the book, or that problem isn't. Now, so it's 1 minus 0.77. Oh, this doesn't get a mistake in it. But I'm not going to make the mistake. All right. So the probability of it not happening, or the proportion of teachers that don't like this, is 0.220503. So I'm going to just multiply those two. So that would be what our numerator is. Then we're going to divide that by 517. And we get a small value. And let's see if it'll let us take the square root without having to write it out. Let's see. Why didn't it let us do that? I'll just have to type it in. So it's 4 zeros. And again, this is what's so crazy about and then you times the 0.96. Nope. Let's back up again. Points. I just wanted to show you this, and like I said, it's intricate on the calculator. You can put it all in as 1 if you want to, but I wanted to show you the in-between. Let's go ahead and just put it in as a whole thing. Just I'll show you, but you got to use parentheses. Now, you got to use parentheses here. So we're going to have 0.779497 times, and what was it? It was 0.22. Do that over here. I should have wrote it down. Point 220.503. You got to have parentheses again, and then you're going to divide by 517. And then you're going to get out of, and there you got the same thing they come up with. So you can do it in one swoop, but you got to use parentheses, because when you multiplying two things up there, you got to do that multiplication first, then divided by the 517, and then take the square root, then multiply times 1.96. All right. So that being said, is The margin of error is 0.035738. Now we just go back and add it to the p-hat and subtract it to the p-hat. So the 0.779497 minus 0.035738 is 0.744. And then adding those two gives you 0.815. You could also look at it like this. So the percentage of teachers who like the game is between 74 and 82%, or the true percentage. So that's all you're doing. Like I said, is here, there's nothing, the only thing that's really new is you're using this different formula for your standard error. Hypothesis test is for next time. Well, now next time we'll just be reviewing, okay? So bring your questions. I'll stick around here. If you've got anything about problem-wise, shoot them to me, all right? So review starting now. Anything that